Hi, let's talk about dry bulk micromachining from this point. Where in dry etching types, dry etching means we do not use any wet chemicals in dry etching. Um, so for the dry etching, we differentiate with the two methods, with the plasma-based dry etching method or without plasma. Okay. And then among plasma-based one, we also have physical ion beam etching, and we have chemical plasma etching, and then we have both, physical and chemical is involved at the same time. So we can kind of differentiate the three different type of plasma-based etching. Um, okay, so we're gonna have more details, but for each types of the plasma-based etching, we have different etchant, like we using ions the momentum actually to etch the certain surface of substrate or materials. And in chemical plasma, we are using the neutral atoms, and then for synergetic way we are using the ion and the neutral atoms together. For these three methods, they have different characteristics of etching. Like a physical ion beam etching, they create an isotropic etching because it's a kind of a physical way, just you using the momentum of the ions to kind of take it out the portion of the exposed area. So because the ions directionality, it caused the anisotropic etchings like a vertical direction. For chemical plasma etching, actually, you can get the isotropic characteristics. For synergetic method, for example, RI, it is a reactive ion etching. Actually, uh, you have combination, but also because of physical way is more dominant, so you can get the anisotropic etching characteristics. Without plasma, you can have chemical etchings, like xenon. I think this xenon F2. For silicon, you have like without plasma, you have that method is available. Okay, well, so when you kind of design the fabrication method, you have a kind of a design whether you want to use the dry etching or wet etching, right? So this is the kind of summarize what is the advantage of dry etching versus the wet etching, and then what is the disadvantages. For dry etching, um, where it is less undercut, right? So less undercut means but this is like a relative advantage over wet etching. In wet etching, you really worry about undercut because you have like over etching, then you always have undercut. But because dry etching, you have like anisotropic directivity of the ion beams, so on. So you have less undercut, right? So that's what you have advantages in dry etching. So it's like a vertical etching is more, whenever you need a really good vertical etching, a dry etching is recommended. For example, you want to have like a higher aspect ratio devices, then certainly dry etching is the way you go. Also, while in dry etching, like this ICP in chamber, basically you have kind of all the gradient on your hands, like gas composition or pressure on the chamber or power, flow rate, everything is under control. So you kind of what you need to know is you kind of find out what is the best combination of those parameters, and then you keep using it for the same parameters to reproduce the same characteristics of patterns. So you have a better control parameters. For word etching, by the way, you have you have a certain, you need to keep certain temperature, and most of the dominant is happen between the chemical reaction between the reactant and then the material that to be etched, right? So these are the less not really good control of parameters. So in terms of control parameters, dry etching is much better. Also, you have less disposal and no bubbles or surface tension problem comparing the wet etching. Disadvantage, certainly you need expensive equipment like this, right? Because some $1 million of the machine that's not easy to have that in kind of in regular lab, and so in clean room, this is really big deal to have those machines, right? Because it's expensive. Also, it's a relatively low slow rate, and also there is a more loading effect. What is loading effect? This is a etch rate variation, a function of the exposed area on the wafer, right? That's loading effect. We discussed couple of slides ago, right? Presentation, my presentation, we talk about loading effect. Also, this is a limited batch process, right? Because the batch process actually, if you have everything done in under the what chemical, you can put the many papers at a one carrier. You can put the many wafers at the same time, and then that's cheaper. But in this case, usually you need to put one wafer sometimes, or a couple of wafers. Most cases maybe up to 4 wafers. So those kind of limitation, that's also limit your batch process efficiency. So that's the one of this disadvantages in dry etching. Also, wet etching causes the smooth surface automatically sharp edges, low cost batch process comparing and dry etching. Okay. Ion assisted etching or vapor etching. Okay. So you have this is like silicon etch rate versus this is time, and this is like a gas that right. And then the XCF2, this is a vapor etchant for silicon. Okay, and then this is what happens if there is only XCF2 gas available or argon ion beam only. But their etch rate is really less. But if they have both together, then you have a higher etch rate, silicon etch rate. Okay, so well, it's really not clear, but those chemical physical synergetic effects, that's actually is crucial. So that's kind of a combination of both will be helpful to have a good etch rate in silicon. And then, before we move on further, we need to talk about the plasma, right? Plasma is like a partially ionized quasi-neutral gas composed of ions and electrons and variety of neutral species in ground and in excited state. So this is very interesting status, right? Okay. So, this means to generate the reactive species and to enhance the etching kinetics. So I mean, the having the plasma has advantages in dry etching, because with help of plasma, actually, you don't need a really high temperature in your dry etching chamber, right? Sometimes without plasma, actually, to have good etch rate, actually, in some cases you need a very high temperature to kind of enhance the etch rate. But with help of a plasma, actually, you don't need to have that high temperature in chamber. You do not want to have a high temperature in your chamber because the high temperature process causes the residual stress at the end. Because let's say you deposit certain material on very high temperature, and then to bring it down to the room temperature, you need that deposited film should be cooled down to the room temperature, right? Then what happens? There is a thermal stress induced during temperature change, right? Then that causes either the deposited film is peeled off or they have a very high stress. Okay, the high stress means the low robustness and then low reliability at the end. The device having high stress, under the high stress, they cannot withstand the tough mechanical condition in operation. So you don't need you really do not want high temperature in the process. Okay, so that's what the plasma comes in. With this plasma, and help the like those process without the high temperature. Okay, so how to make a plasma, right? You have two ways with DC plasma or AC plasma. Basically, you need two electrode here, and then you apply the high voltage like 1.5 kilovolt with certain separation, um, and then the inside there is the inert gas or either argon, like argon is filled in with the at the low pressure. Then if you keep you keep increasing the voltage, then there is a grow discharge between the two electrode. Okay, so now when you have plasma, then they're very bright, like a UV light, like a it's very shiny beam is coming kind of grow inside. Okay, so those the things that kind of a way to generate the plasma. Then so that's what this is kind of process that plasma formation here. Okay, so with this condition, then you have like this is a kind of a ideal condition. You can enhance the etch rate under this plasma. Okay. So this plasma physics, I'm not going over in detail, but this is like the way between the cathode and anode, this is a physical distance, and then there's a way the plasma grow here. How can we use this plasma for dry etching? The substrate to be etched is placed on the cathode. In the plasma, and the physical and chemical etching can be induced. So you can place your substrate on cathode, and then this plasma enhanced process could be done. RF plasma physics. So now you have like AC RF plasma comes in, then you can generate RF plasma as well. Okay, so I'm not going to go over in detail, but this is another way you can you can create the plasma. Okay, etch chemistry. All right, so this is for the silicon etching, right? For silicon etching, you need either CF4, SF6, or Cl2. This is gas, you need to have it, and this is plasma based method. Okay, and then I'm not going to go over in details, but these are the gas, and then the those recipes are available in plasma enhanced machines. So when you have like purchase the plasma enhanced dry etching machine, actually the vendor like applied materials, they already set up certain the recipe that for the various materials. So actually you can have their own you can get their recipe, and then you can use their recipe, to or adjust the recipe to have that particular etch characteristics in your application. So that's what actually the applied materials is famous about. Okay, they are not just selling the equipment only. They are selling what they are claiming is they are selling technology, right? They are selling machine plus some know-how or recipe that the customers are asking for. Okay, that's why the applied materials are so successful. Okay, I have chance to visit the applied materials in Santa Clara in California, and then I see too many application engineers, and then the fabrication process engineers actually work very hard, uh, and that's and that they have a kind of particularly strong point in that portion. They have a very good interaction with the customers, and then they know what is the customer's need from that machine. Okay, and then their engineers, process engineers, and application engineers, they work together, right, to find out that magic recipe that the customer looking for, and then they are selling those uh, magic recipes with a machine. Okay, so in that way, you can hold the customers, that to let them keep using their machine for a long time, right? As a process, as a like a recurring users, and and when I was in PhD student, I really have lots of time to be spent to just figure out the ideal recipe. Um, Many trials, errors, and we are not really good in those some chemistry, and then we have too many combination like power and pressure and temperature, gases, and so many. So just to given the machine is not enough. You have certain kind of idea what is good starting point to figure it out the best or optimize the process for your particular material. Okay, so that's the that's the applied materials is good about. So so that's what actually I contact the those vendors of machine, and then to get those the recipe. Otherwise, it's a really demanding work to get the recipe. So that's kind of a chemistry. Or depending on additives, there is a etch rate and selectivity change. For silicon substrate or silicon dioxide, depending on percentage of oxygen, okay, their etch rate actually is coming up and down, right? It seems there is like a ideal percentage of oxygen, right, to be etched, right? This is the let's see, okay, the CF4 and O2 mixture. So this is like dry etching for silicon or silicon dioxide at that particular condition. This is the pressure, and then this is like a power between the two electrodes. This is temperature, right? In that condition, just change of the percentage of oxygen, this is a really dramatic change of the etch rate, right? So that's what you can feel it, right? You need to find out those magic point. Otherwise, your etch rate is really slow. Then, right? Then you can imagine that let's say you failed this process. Then what happened, right? You should start from the beginning, right? Right? That's the lots of work done, right, already, but you should repeat to get that point again, right? So that's the really hard. That's a really hard time in cleaning. Same as the etch rate in CF4 and H2 mixture. This is percentage of hydrogen in their mixture. By change of this hydrogen percentage, you see the silicon dioxide, the polysilicon, and the photoresist, the etch rate is different, right? So, okay, etch chemistry others and put oxide film or nitride film, uh, similar to silicon etching chemistry, but you may need a different, you may need a good photoresist mask, and then again, as you've seen the previous slide, you need oxygen to increase the etch rate or decrease selectivity. Organic materials, oxygen necessary, and then mask is those are the good, so on. So let me skip it. Okay, and isotropic etching. Okay, here, let's say as the concentration of F, right, fluorine fluorine increased, the H increased, and then become the more isotropic. Okay, so that means it's more chemical than physical. Okay, okay, well, so over here, right, well, there is a mask here, and then this is like a silicon, this is silicon dioxide, and then, well, effect of a bias voltage, right? What the bias voltage between the two electrodes, it could be somewhere in between the 0 to 200 volt. Then the etch rate, right? The etch rate could be changed like for the silicon, with a higher bias voltage, you have like huge etch rate, and then the no bias voltage, for example, right? For silicon etch rate, and then okay, and then well, also to have that well, you have if you have different combination like of gases, and then you can get either um, isotropic and anisotropic etchings, right? That's like vertical anisotropic etchings, and this is like a they have a different like etch rate. And this is a purely vertical, but this is also attached to the sidewall as well. So that's you need to find out kind of magic here. For example, if you have no bias, and then if you choose like a 10% of hydrogen in CF4, right, over here, then you have got the what happened? You have got the zero silicon etch rate. Okay, and but over here, so Vx is zero, and but V0 is you have good etch rate. That means there is no X direction etch rate. So with this process, you can get this, right? Because no X direction etch rate. X direction is like this is X, right? This is only vertical. So if you want to have this kind of pattern, right? This is a good magic point, like a 10% of hydrogen, right? Then you have Vx is you have Vg, but you don't have any Vx at that point at the particular point. At the other location, you have like this like undercut, right? So those things are very interesting in dry etching. Okay, etch parameters and their effect in plasma processing. So when you figure it out, those operating variables like power, pressure, gas flow, gas composition, um, and then the outcome is likely like if you increasing the power, for example, this is the black arrow, then you're likely going to increase the electron impact or reaction rate, and the electron energy distribution function is increasing, and then electric field distribution will be increasing. Then at the end, your etch rate likely increasing. Uniformity will be increasing, and isotropy will be increasing. Your selectivity will goes down, and then your radiation damage will goes up. Right. So there's those kind of idea, right? If you have just check the outcome how they looks like. If you don't like the H rate, then this is combination. If you don't like the H rate, you want to increase the H rate, then try to push the power up. But after push power up, maybe your selectivity goes down, or you have a unwanted n asterisk goes up. Then what you can do is you pressure up, then those then n asterisk will be goes down, right? So those are the kind of combination actually you can play with it to get the optimal recipe, right? Okay, let me stop here and then let's continue the next slide.